All right. Good morning, folks. We're going to go ahead and get started here. I'm going to we're going to take a look at the 13.5 notes from yesterday, and we're just going to do a quick refresher of what we covered yesterday, and then we're going to pick up where we left off. So hopefully the technology is cooperative today. All right. Seems like we're off to a good start. Fingers crossed. Okay, so yesterday we talked about calculus and polar coordinates. Specifically, we talked about tangents with polar coordinates and how if we wanted to find the slope, we needed to use this particular formula. And then we took a look at an example of how we could just use the formula to determine the slope of the curve at a given angle, and that it was a lot of algebra and plugging things in and just making sure that we accurately compute the values. But there wasn't really anything special other than plugging numbers into the formula. Okay. And then we did the same thing here where we took a look at equation. We were able to sketch a graph of the equation without using a table. And again, that's a skill that a lot of the Calc 3 professors like you to have, which is why I'm kind of pushing it a little bit. And then we were able to find the slope again in part B. But at the end of class, we extended that so that we could determine where this curve has horizontal tangents and where the curve has vertical tangents. And so we talked about how the numerator being set equal to 0, like that pink part, is where we know that the curve has horizontal tangents. And then the green part is where the denominator was equal to 0 because that causes a curve to have vertical tangents or undefined tangents. And at the end, not only did we need to know our unit circle values to get the correct answer, but we also needed to know when things were or were not differentiable. Okay, so thinking back to the beginning of Calc 1, where we learned about things like corners and cusps being situations where we cannot take the derivative. And so at those points, we need to exclude those from our answers, even if they come up from our equation. All right, so that was using derivatives of polar coordinates. And then at the end of class, at the very end, we walked through one example kind of quickly about the area that we could find using polar coordinates. And we talked about how instead of starting at a value along the x-axis and then moving to a value on the further down on the x-axis, that we actually had a starting angle and an ending angle. And that was our bounds. And so knowing what values to plug in for the bounds, that's something that we'll talk about a lot more today. It's something that comes up in the quizzes. You can always go back to the tables to help you out with that, but I think it does take a little bit longer that way. But at this stage, if that's what you need to do to make sure you get the right answer, it's not a bad strategy to have. Okay, so here was our example that we had at the end of class. So we took a look at the cardioid that we were familiar with from earlier in the lesson. We knew that it was cosine, which meant it was symmetric about theta equals 0. And then we set up our integral using the formula, and then we solved. And at this point, we've seen this substitution so many times. So I hope that's becoming a little bit more second nature to us, that anywhere we see that cosine squared, that is something that we are unable to integrate without making a trig identity substitution. And what we substitute in for that is 1/2 1 plus cosine 2 theta. And the cosine 2 theta is something we can integrate. So that's just going to be a u sub situation, which makes our lives a lot easier after we get to the integrating stage. And at the end, you still need to know all of your trig values to substitute in what is sine, what is cosine of certain values on the unit circle. So we still did need that to get our final answer. But at the end, our answer was 6 pi for the area inside of this cardioid. Okay. And that's where we left off yesterday. So based off of what we covered yesterday for 13.5, are there any questions coming up for folks at this point?
Yes, I do have a question.
Okay.
About the differentiable. So let's say the heart was pointing up.
Yeah.
I will say that it won't be differentiable at pi over 2.
It depends what value is going to give you a 0.
So
right?
if my 0 will be pi over 2, then I will just have to say that it's not going to work.
Right.
Okay.
Okay. So to kind of reiterate her question, because I think it's a really good one, like this point right here, okay, that has an R value of 0. So you want to look for whatever angle gives you an R value of 0. Those are the places where it's not going to be differentiable. Okay. Thank you for asking that question.
I have one question, but it's on the quiz, so I'll just ask you after class.
Okay, sounds good.
All right.
Professor, I have a question.
Okay.
Can you explain again how you got the 1/2?
The 1/2.
Top. Yeah, can you just kind of go over that one more time?
It's just the identity. Cosine squared is 1/2 1 plus cosine 2 theta.
Okay. All right. Got it.
So the whole thing in yellow, that's a substitution.
Okay.
Okay.
Perfect.
You're welcome.
Thank you.
And I also have a quick question. So in regards to the cusp, right? So it's pretty obvious that cardioids have that little cusp, but the inner loops also would have a cusp at that point, correct? Because even though it kind of transforms into the other one, or is it not considered a cusp at that point?
It's not considered a cusp because it's not like we draw it like we draw the cardioid and then we add the loop. Okay, so they're not like sort of two separate things, but rather what happens is you draw your cardioid, but then it kind of comes right in and loops around itself.
Okay, yeah, that makes sense. I just wanted to make sure.
Yeah, so it's really the cardioid that has that point of, and then I think someone had asked about the dimpled limason. I believe the dimpled is also not differentiable, but I'm going to double check on that today. But the convex one should be differentiable.
Okay. Thank you.
Mm-hmm.
Can I ask one thing since we're talking about the points that aren't differentiable? Are we just looking at points where there is an instantaneous like change in direction kind of a thing where it's not like a continuous line going, but once it hits a point and then all of a sudden takes a hard left, then so those are the points where we would sit there and make sure that those are out of our answer.
Right. And your Calc 1 professor probably drew a diagram like this at some point where they were like, okay, so, here's an absolute value graph. And like, can you find the slope at different points? And like, here you can find the slope, here you can find the slope. And on the right-hand side, you can find the slope at all those points. But then what the question is, right at the corner, I could draw a tangent line like this, but I could also draw a tangent line like this, or even in the negative direction. So because there are an infinite number of tangent lines at that point, we consider it to be not differentiable. Right, exactly, Mariah. It's because they have more than one possible tangent line. And so the corner is one example, but the cusp also models that. So if I have a cusp and I want to think about a tangent line right here, I could have one like this, or I could have one like this, and I could have an infinite number of ones in between, so that it's not getting to be a certain tangent line. I think one of the weird things about calculus is you start by talking about all of these big concepts, and I feel like it's just such a rough transition from like all the calculating that you've been doing. But yeah, it does kind of come back that like sometimes these answers aren't actually answers. It kind of depends on our picture. So with that being said, let's move on to what happens if we have we want to find the area, but only of part of the graph, okay? And so given our example number 4, it says find the area bounded by the inner loop of r equals 2 plus 4 cosine theta. And so when we're thinking about this one, the 2 and the 4, we know that that's going to give us an inner loop, right? Because we have 2 divided by 4, and that equals 1/2, and that is a situation where we know our limacon is going to have an inner loop, okay? Now, in terms of thinking about how we figure out the angles, right? Because we kind of know that our picture is going to look something like what I tried to draw earlier. Something like this, right? So then how do we know what angles stop and start to give us this region right here, okay? And it does kind of come back to the idea that we're looking at where our function, our r function, or our f of theta, where that equals 0, because right at here, it has an r value of 0. And so at the start of the loop, the r value will be 0, and at the end of the loop, the r value will be 0, okay? So the r equals 0 at the start and stop of the loop, okay? So that's the idea that we're going to use to help us find our bounds. So to find our bounds, we're going to take our r, which is 2 plus 4 cosine theta, and we're going to set it equal to 0. Okay. And so we do a little equation solving. We end up with cosine theta equals -1/2. Okay. And then our job is to find the angles on the unit circle where cosine of that angle is -1/2. And so we'll end up with theta equals 2 pi over 3, and theta equals 4 pi over 3. Okay. Are there any questions how we set up or found those angles?
I just have a question about how we format our answers.
Okay, well, let's save that until we get to the answer then.
Okay.
Okay. All right, so if we want to find the area, we got to write our area equation. So area equals 1/2 the integral from alpha to beta of r squared d theta, okay? And again, the alpha and beta, it's like the a and b, but we're just considering angles, so we use alpha and beta instead of a and b. And again, some textbooks keep the 1/2 inside the integral. It's up to you whether you keep it on the inside or the outside, but a lot of times it kind of gets like we're able to cancel that away with all the coefficients that are inside. So it's not really that big of a deal either way. So if we fill in our equation now, we've got 1/2 the integral from 2 pi over 3 to 4 pi over 3. Of r, which is 2 plus 4 cosine theta squared, because I need r squared d theta. Now, this is going to require us to FOIL. We want to make sure we FOIL and that we don't just distribute. And that'll give us 1/2 the integral from 2 pi over 3 to 4 pi over 3. And if we FOIL this out, we'll get 4 plus 16 cosine theta plus 16 cosine squared theta d theta. And I do see that there, I could pull out a 2 out of everything. In fact, I could factor out a 4 out of everything if I wanted to. I think in my notes, I just distributed the 1/2 back in and reduced everything by a factor of 2, but it doesn't really matter. So if we get rid of that factor of 1/2, we'll get 2 pi over 3 to 4 pi over 3 of 2 plus 8 cosine theta. And then plus 8, right? Because 1/2 times 16 is 8. But because I see that cosine squared, like I saw in the earlier problem, we're going to substitute that right out with the 1/2 1 plus cosine 2 theta. Okay, so we did kind of a lot in one step. We distributed that 1/2 in, so that's why all our coefficients are half of what they were, and we made a cosine squared into 1/2 1 plus cosine 2 theta. Okay. So from here, it's just a matter of distributing everything and taking our integral. And so what do we end up with? We end up with 2 pi over 3 to 4 pi over 3. And we get 2 plus 8 cosine theta plus 4 plus 4 cosine 2 theta d theta. And we can combine the 2 and the 4 to make a 6. All right. So when we integrate now, we have 6 theta, because 6, when I integrate it, gives me 6 theta. The integral of 8 cosine theta gives me 8 sine theta. And the integral of 4 cosine 2 theta gives me 2 sine 2 theta. And I'm going to plug in 4 pi over 3 and 2 pi over 3. And when I plug those in, I do have to plug in both bounds because they're going to generate different values. Okay, so let's plug in the 4 pi over 3 first. That will give us 4 pi, that'll give us 8 pi plus 8 times sine of 4 pi over 3 is negative root 3 over 2 plus 2 times sine of 8 pi over 3 gives me root 3 over 2. So all of that is when you plug in 4 pi over 3. And then we have to subtract what happens when we plug in 2 pi over 3. And so that's going to give us 4 pi plus 8 times sine of 2 pi over 3 is going to be root 3 over 2 plus 2 sine of 4 pi over 3 gives me negative root 3 over 2. Okay. And when we combine all of our terms here, I like to combine terms that are like first. So for example, I have 8 pi minus 4 pi. I know there's going to be 4 pi left from that when I subtract. And then I reduce a bunch of things before I multiply out. And that's one thing I noticed when I was grading some of the exams is some of us are trying to just like work with these giant numbers, but I would really encourage you to reduce before you multiply. The point of making it no calculator is not to see how well you can multiply, but can you be savvy and efficient with your mental math, okay? So for example, 2 and the 8 reduced to 4. This 2 and that 2 reduced to 1, reduces to 1, reduces to 4. Okay, so as soon as you get rid of some of those values and reduce it, you'll end up with a lot smaller numbers, okay? And so what does this give us? This gives us -4 root 3 plus root 3 over 2, or root 3 minus, and then plus. And I believe that gives us -6 root 3. What is this? 4, -4 plus 1. Or does it give us 2? 2, I think. I think that's right. All right, so the only difference between the example we finished off yesterday with and the example we started this morning with is that the bounds in the first one, yesterday's, just required us to go one time around the unit circle, 0 to 2 pi. But in example 4, we had to find where our alpha and beta was before we were able to start the problem. Okay, so this side piece over here, this is the difference between example 3 and example 4. Okay. Mariah, you said you had a question about the answer.
I was just curious if when, like, part of the question is what angles, right, and where like theta is. And then did you want us to put those, box those in? And if so, do you want them in like smallest to biggest order? Because I remember in the past, professors wanted it in a certain order.
I don't care.
Okay.
I don't. I think for WebAssign and or other online platforms that grade automatically, they ask for the smaller one first and the larger one second, but it doesn't matter to me.
Okay, because that was always really annoying online where it was like a technical how you formatted it wrong.
Right. You're still submitting your work for the test. I'm still grading your work for the test. So it's not just based on your answers. You're submitting a file that has your answer. You're not typing anything in.
Yeah.
Okay. All right. So, whoop, slide is so big. Okay. So moving on. We have seen situations where we know how to find the integral between just one curve and the x-axis. So after you learned how to do that, you also learned how to find the area between two curves. And so between two curves meant that you had an upper function and a lower function. And then you would just do top minus bottom to find the integral of that area because you wanted to find the distance between the two lines or the two curves, okay? And then sort of an extension of that was, well, what happens if our curves are more like left and right rather than up and down? And in that case, we said that you take the right function and you minus the left function so that we could find this distance, this vertical distance between the two, or the horizontal distance between the two vertical curves, okay? And so now we're going to take that same idea and we're going to apply it to polar situations, okay? So specifically, we're looking at a case where we might want to find the area between two curves, okay? And we're still going to keep the idea that we have sort of an outer function and an inner function. And so you can see that the letters that they use right here actually incorporate that right into the formula. Okay, so you've got this red curve and they call it R sub O, O for the outer function. It's not a 0, okay? And so that would be what goes here. So the outer function squared. And then they have the inner function, the one that's closer to r equals 0, and that's in the blue. And that's what gets subtracted and squared. Well, squared and then subtracted in the area formula. Okay, so this is kind of like washer method, where you have the outer function squared minus the inner function squared, okay, except that there's no pi, because we're not really thinking about the volume here. We're not looking at like the area of a circle. We're just looking for the distance here. So it's kind of like washer method, but it does not find volume. So knowing that, let's take a look at 2 examples and how we can set up and solve. And again, I think this will be helpful in how we find our intersection points and how we find the angles that tell us our bounds. What are our alpha and our betas? All right. So if you like the quality of these graphs, I made them on Desmos. All I did was type in r equals 2 plus 2 cosine theta and r equals 3, and this is the picture that popped up, okay? And so if you want to use this to support your work in your quizzes, you're more than welcome to do that. But you will not have access to Desmos for an exam, so I don't want you to be reliant on it, but if you like a nice, neat diagram, this is how you get them, okay? And so we've got our red curve is our cardioid, our good friend 2 plus 2 cosine theta. And then our circle is our r equals 3, and that's our green circle on this grid. And so I've broken this up into a few parts. Okay, so I have the graph, but I'm asking us to find the intersection points. And I just want to clarify, when I say find intersection points, like I want us to find it algebraically. I don't want us to guess and check and be like, oh, I got the right answer. Like find it algebraically, okay? And then underneath, we're going to answer 2 different parts. We're going to find the area that is inside the cardioid and outside the circle. And we're going to go through that integral. And then we're going to set up, but we're not going to solve the area that is outside the cardioid and inside the circle. Okay? So that's where we're headed with this problem. So in order to start, we need to find our intersection points so that we can find our alpha and our beta. And if we look at our intersection points, okay, here's what we find. That here is one intersection point. Excuse me. And we're looking for where the green curve, and the red curve are the same. And if we find our other intersection point, that means the same thing. Where does 2 plus 2 cosine theta equal 3? And so that's where we're going to start by our setting up 2 plus 2 cosine theta equals 3. Okay. And we're doing this again because we want to find where the 2 curves are equal to each other. And so we'll do a little manipulation. I'm going to subtract the 2. I get 1, and I'm going to divide by the 2, and I get cosine theta equals 1/2. Okay. Now, cosine theta equals 1/2 means that I'm not looking for the same answers as last time, but rather I'm looking for the ones where the cosine is a positive 1/2, not negative. And so that's going to happen at pi over 3 and 5 pi over 3. This top coordinate has a theta of pi over 3. What is the r value?
3.
3, very good. How'd you get that?
Because we are talking about the circle. The green line is the circle and the radius is 3.
Exactly, right? So we have r equals 3. And sometimes we're just like we think it must be so much harder than it is that we like overthink too much and we panic a little bit, but sometimes it is as simple as it's on the circle and the circle always has an R value of 3, okay? That means down here for the second point that R value is also 3, but this angle is 5 pi over 3, okay? Now, just to kind of plant the seed, what is another name that I could call that bottom point?
Negative pi over 3?
That's 3 comma negative pi over 3. Okay, so that's another name that we could give that same point. Okay, so let's read that second part now. It says find the area of the region inside the red curve. So inside the red curve and outside of the green curve. And so let's shade that in a pretty color. So let's get that region. We're going to shade that region in the light blue. And that's going to be sort of like this moon slice looking thing, like when the moon is not close to being full, but it is almost like a sliver. Okay, so that's the area that we're looking for. It is outside the green circle and inside the red cardioid. And so in order to set up my area, okay, in order to set up my area, I want to follow the same equation that I had from above. And so that is area equals 1/2 the integral. And we're going to leave the bounds for a moment, okay? And the outer curve, I think we would all agree, is the cardioid. So 2 plus 2 cosine theta. And I need to square that because that's R sub 0 squared, or R sub outside squared, minus the R inside, or the inside function, is 3. And we square that. And then we seal it off with the d theta, okay? I know we're doing a lot of writings for these problems. Please make sure that you have a dx or a d theta or d whatever you need at the end of your integrals. But here's our formula. Now, if I think about going around the unit circle, okay, I know that we count in this direction. And so if I pick my bounds as pi over 3 to 5 pi over 3, I would actually get this region. Because I would say, let's start here and let's stop here. That makes sense?
Yes.
Yeah, okay. So if I use the pi over 3 and the 5 pi over 3 that I got from my answer, and I think about what it looks like on my diagram, I would be finding the other region in between. I would not be finding the blue region that I want to find, okay? So that means let's keep that in mind for the last part where we have to set up the integral. But since we want to find the blue region, and I know things travel in a counterclockwise direction, I would have to start down here, go this way, and end here. That seem logical?
Yes.
Yeah. Okay. So the direction helps with that starting point and stopping point, okay? So based on that, we're not going to use pi over 3 as our bottom bound and 5 pi over 3 as our top bound, but we're going to use negative pi over 3 as our bottom bound and pi over 3 as our top bound, okay? This is one of the things that I'm really looking for, like on an exam or on a quiz. I want to make sure you have that setup right, okay? I want to make sure that you have the setup right, because if the setup is wrong, even if you get the correct answer, like it was more like a few wrongs made a correct, not that you actually set it up in the right way, okay? So let's see, I saw a question with the bounds being pi over 3 to negative pi over 3. We always put the smaller one on the bottom, so it should be negative pi over 3 on the bottom, Patrick.
So that's why you planted the seed with the negative pi over 3?
Yes.
It's a sapling now?
Yeah. All right, question for you guys. This blue region, symmetric or not symmetric?
Symmetric.
Symmetric. Okay, where can I cut that region in half? At what angle?
0.
0. Okay, so I'm gonna do that. I'm gonna change my bounds to be from 0 to pi over 3. And I'm going to double it, which means double 1/2. It just goes to 1. All right. And then while I am here, I don't know why my handwriting's bothering me today, from 0 to pi over 3, let's FOIL out everything we have and see what we get. So we get 4 plus 8 cosine theta plus 4 cosine squared theta, that's my r sub outside, minus 9, that's my r sub inside squared, okay? And I do think that you guys have actually been really good about like the foiling. I haven't seen a lot of the whole, oh, I'm just gonna distribute the power, so maybe I'll just stop mentioning it so we don't do it anymore, okay? But from here, I noticed that everything is okay to integrate except that cosine squared, right? And so we know that that's a swap we need to make. We need to replace that with 1/2 times 1 plus 2 cosine theta. And so when we do that, we will get the integral from 0 to the pi over 3 of 4 minus 9 is negative 5 plus 8 cosine theta plus 4 times 1/2 is 2. 1 plus cosine 2 theta. And I'm going to take this negative 5 and this 2, right, because I need to distribute that and combine those. So we'll go from 0 to pi over 3, negative 5 plus 3, or negative 5 plus 2 is negative 3 plus 8 cosine theta plus 2 cosine 2 theta d theta. All right, so let's integrate. We've got negative 3 theta plus 8 sine theta plus 2 and 1/2, that's going to go away, and I'll have sine of 2 theta. And I'm going to plug in pi over 3, and I'm going to plug in 0, okay? And when I do that, I end up with, so I already can see that when I plug in 0, everything's going to go away. So the only thing I'm going to show is when I plug in pi over 3. So I'll get negative 3 times pi over 3 plus 8 times sine of pi over 3 is root 3 over 2 plus sine of 2 pi over 3 is also root 3 over 2. Look to see if there's anything we can reduce before we get started. So I see that this 3 and this 3 will reduce to a 1. All right, so I have a negative pi here. Now, I'm not going to cancel the 8 and the 2 only because I see that I could combine it with that 1 next to it. So I have like 8 root 3s over 2s, and then I have 1 more of them. So that's going to give me 9 root 3 over 2. And then I have my minus pi from inside that circle. And so this is the area of that little blue sliver. Okay.
Professor, I have a question.
Yes, ma'am.
So I think I'm missing something from CAC 1. Can you explain why sine of 2 theta, which is here sine of 2, and the pi over 3 is the square root of 3 over 2?
Sine of 2 pi over 3, because I plug in pi over 3. Right? This is sine of 2 pi over 3 when I plug in pi over 3.
Oh, okay, thank you.
Okay, yeah, and then it's just our unit circle value over here. It's not
Yeah.
anything fancier than that. I literally just plugged in pi over 3.
I'm sorry, thank you.
No, you're fine, you're fine. I think sometimes we're just learning all these things that we're like, oh, it has to be harder than I think it is. Okay. Does that make sense to everybody else why it's root 3 over 2? We don't have to use any double angle identities or anything. Okay, so let's do this then, and then we'll take an earlier break today. Let's set up the integral to find the area of the region outside the cardioid and inside the circle. So let's pick a different color for that one. Go with a light purple. And let's go back up, and we're going to shade the region outside the cardioid, but inside the circle. So outside the cardioid, but inside the circle is going to give me this region over here. Okay. So outside the red, inside the green, but this region is what we kind of talked about earlier, where we said if we go in the direction of our unit circle, right? If we go in the direction of the unit circle, we would start here, which means pi over 3 would be my bottom bound for the purple part. And then I would stop here. So 5 pi over 3 would be the top bound for the area of the purple part. Okay, so that's the difference between getting your bounds correct for this blue region and getting them incorrect. Like if you use the wrong values, you're actually finding a different area. And it might work out that they happen to be the same, but most of the time they're not the same. So we really want to make sure that we know where to start and where to stop. So if we go back down and set up our area.
Professor?
Yes.
So if we were to flip the bounds of integration like you're mentioning, would that basically find us the area if it was like flipped? So like the cardioid was flipped to the other side, basically?
No, if we, I don't think I understand your question.
Like, because if we switch the areas of like bounds of integration, correct? Right? So instead of writing pi over 3 on the bottom and negative pi over 3 on the top. Oh, never mind. You know what? I just realized my brain just completely, never mind. Never mind. I just realized my mistake. Never mind.
Okay, no worries. I feel like this morning I was walking my dog and I was like, oh, today's Thursday. I was like, it is not Thursday. We have 2 more days of lecture, but I feel like my brain is a mess too. So we're all in it together, folks. All right, so this area of the region outside and inside, I need my 1/2 because that's part of the formula. I know I'm going to start at the smaller value of pi over 3, and I'm going to end at the larger value of 5 pi over 3. And then because my formula has to be the function of the outer one minus the function of the inner one, okay? If we look back at the picture, that has changed now. The green one is on the outside and the red one is on the inside. So if you use the same integral as you did from this part, you'll get an incorrect answer. All right. So it's still got to be the outside squared minus the inside squared. So we're just going to switch them. That'll give us 3 squared minus 2 plus 2 cosine theta squared d theta. Okay. So we have a new outer curve, we have a new inner curve, and we have different bounds. But other than that, the structure is very similar. Like if we wanted to solve this one, we would be able to use the same strategies that we used from the previous part, same substitutions, same kind of process. Okay, so that cosine squared going to cosine squared theta going to 1/2 1 plus cosine 2 theta is a pretty valuable substitution to know. What's the sine squared one?
Is that 1 minus cosine 2 theta?
Exactly, it's the same thing. It's got the 1/2, it's got the 1 and the cosine 2 theta. The difference is it has a minus sign in there, okay? So I thought we would use all the cosine ones in the lecture, but you might have some of those sine squared ones in the quiz and on the exam. So just know it's the same thing, except the sine squared has a minus sign in it. Okay.
Can I ask a question?
For sure.
So with the integral that we just set up,
Yes.
are you able to use symmetry on that once again in order to get rid of that 1/2 in front?
That's actually a really good question. I meant to talk about that. So I think for this middle one, I would 100% use symmetry because
One of the plugins is 0.
I get to plug in a 0, right? If I wanted to split the bottom one into a symmetric one, I could say the integral from pi over 3 to what's halfway between pi over 3 and 5 pi over 3?
I would say pi.
Yeah, it's going to be pi. So there's nothing wrong with writing this instead, if you like the idea of symmetry. I think for me, it's a toss-up whether I plug in all my trig values, because I'm still going to have to plug in trig values, but some of them might go to 0 with the pi's. So I think that it's possible that the bottom one could save you a little bit of time. Maybe it's not as obvious as if you plugged in 0, but I think it might still be a little bit of a time saver.
Okay. And then my very last question. So for this function, we have 2 plus 2 cosine of theta.
Yeah.
If our theta had an n in front of it, would our bounds just change? Like, let's say it was negative pi over 3 to pi over 3 for the middle one, but it was 2 plus 2 cosine of 2 theta. Would you just divide both of those bounds by 2, and then those would become your new bounds? I don't know if that made.
Sorry, can you repeat that?
If your equation changed to where you had a 2 plus 2 cosine of 2 theta.
Oh, I see. Like that?
Yeah, would your bounds just have to be halved whenever you plug them in? So it would be negative pi over 6 to pi over 6?
Why don't you play around on Desmos with that? Actually, let's plug that in and see. Okay, so 2 plus 2 cosine 2 theta. Okay, so if you go to Desmos. Okay, so first of all, if you want to plot polar, if you go to this little wrench in the corner, then you click the polar one, it'll give you a polar graph. And we can type in R equals 2 plus 2 cosine 2 theta. So you get something kind of like that, right? So it's useful to generate the graphs, but do you guys see where it has like underneath the equation on the left-hand side, it says theta, and theta is between 0 and 2 pi, okay? So if I change that, so what was your guess? That it would be pi over 6? If I change the bottom bound to be negative,
I just realized that putting that 2 in front of the theta completely changed my entire graph.
right, exactly. It's not going to be the same graph because you have, yeah, so pi divided by 6. And then let's change this to be pi divided by 6. So that's the part of the graph you get when you plug in negative pi over 6 to pi over 6 as your bounds.
Got it.
Okay, so if I were working on a quiz question, and let's say I had 2 plus 2 cosine theta, and I solved it using the algebra we just did, but then I was like, I want to double check my answers, I would plug in negative pi over 3 to pi over 3. Am I missing something here? It should give us the whole, oh yeah, because it's just that part right there, right? So that was the part of the circle, or the cardioid, and then we could have our equals 3. That would give us the circle part. And same thing if we plug in negative pi divided by 3, and oh, that's only going to change your r, not your theta, because you don't have a theta in there. But you can see that that gives you the little region that you're looking for.
Yeah, I can see it.
Okay. So it is a pretty handy tool. I would encourage you to maybe just use this as you're going through your quiz to help you confirm your answers, especially in a world where I feel like sometimes we don't really know if our answers are right or not. We just kind of hope for the best sometimes. This is one way that you can kind of say like, all right, I solved it algebraically, and I can see on the picture that what I have is the correct answer, okay? So this seems like a good place to take a break. So we're gonna pause here. Let me stop this. I'm gonna stop the recording.